Tonight, we are going to ask, is the universe alive? Now, your first reaction might be to say no, obviously not. The universe is a collection of matter and energy, of atoms and photons and electromagnetic fields, governed by impersonal laws of physics. It does not eat. It does not breathe. It does not reproduce. It is not alive. Case closed. Welcome. Settle in. Let the tension in your shoulders release. Let your jaw unclench. Let your breathing find its own slow, comfortable rhythm. Tonight, we are going to ask a question that might sound strange at first, maybe even absurd. But as we explore it together, gently and without rushing, I think you will find that it is one of the most fascinating questions. But let us not close the case so quickly. Because the question of what it means to be alive is far more complicated than it seems. Biologists have been arguing about the definition of life for centuries, and they still have not fully agreed. And when we look at the universe through the lens of physics, through the lens of complexity and thermodynamics and information theory, something remarkable begins to emerge. The universe does things that look, in surprising and unsettling ways, like the things that living systems do. So tonight, let us hold the question open. Let us explore it from every angle. Let us see what science has to say, and let us see where the wonder takes us. There is no exam at the end. There are no right answers to memorize. Just ideas, gently offered, as you drift toward sleep. Before we can ask whether the universe is alive, we need to ask a more basic question: what does it mean to be alive? What separates a living thing from a dead thing, or from a thing that was never alive at all? This turns out to be a surprisingly difficult question. You might think that biology, the science of life, would have a clear and universally accepted definition of life. But it does not. There is no single definition that all biologists agree on. Instead, there are lists of properties that living things tend to have, and different scientists emphasize different properties. The most commonly cited properties of life include metabolism, the ability to take in energy from the environment and use it to maintain internal order. Growth, the ability to increase in size or complexity over time. Reproduction, the ability to create copies of oneself. Response to stimuli, the ability to detect and react to changes in the environment. Evolution, the ability to change over generations through natural selection. And homeostasis, the ability to maintain a stable internal state despite changes in the external environment. These properties work reasonably well for the organisms we encounter on Earth. A dog is alive. It metabolizes food, grows from a puppy to an adult, reproduces, responds to its environment, evolves over generations, and maintains a stable body temperature. A rock is not alive. It does none of these things. But the boundaries get blurry. Viruses can reproduce, but only by hijacking the machinery of living cells. They do not metabolize on their own. Are they alive? Fire consumes fuel, grows, responds to its environment, and can spread to create new fires. Is fire alive? Crystals grow and can replicate their structure. Are they alive? Most biologists would say no to all of these, but the reasons are not always clear-cut. The line between living and non-living is not as sharp as we might like. And this is important for our question tonight. If the definition of life is fuzzy, if the boundary between alive and not alive is blurred, then the question of whether the universe is alive is not as ridiculous as it might first seem. It depends on where you draw the line, and on which properties of life you consider most essential. The physicist Erwin Schrödinger, one of the founders of quantum mechanics, wrote a famous book called What is Life? In 1944. In it, he approached the question not as a biologist but as a physicist, asking what makes living matter different from non-living matter in terms of the fundamental laws of physics. His answer was remarkable: life is a system that avoids the decay into equilibrium. A dead body decays. A living body does not, at least not while it is alive. Life is a process that maintains order, that fights against the natural tendency of matter to become disordered. Life, Schrödinger said, feeds on negative entropy. It takes order from the environment and uses it to maintain its own internal structure. This definition is much broader than the traditional biological one. It does not mention DNA or cells or reproduction. It focuses on the fundamental thermodynamic character of life, the ability to maintain order in a universe that tends toward disorder. And by this definition, many systems that we do not usually think of as alive begin to look lifelike. A hurricane, for example, maintains its structure by feeding on the energy of warm ocean water. A star maintains its structure by feeding on nuclear fusion. The Earth maintains its temperature by regulating the flow of energy from the Sun. None of these systems are alive in the biological sense. But they all share the fundamental thermodynamic character that Schrödinger identified as the essence of life. This broader view of life opens the door to our question. If life is fundamentally about maintaining order through energy flow, then the universe as a whole, which has been creating increasingly complex structures through the flow of energy for nearly 14 billion years, might qualify. Not as an organism in the biological sense, but as a system that does what life does, it creates and sustains order in the face of entropy. Let us start with metabolism. Living things take in energy from their environment and use it to maintain their internal structure. Your body does this constantly. You eat food, your cells break down the molecules, and the energy released is used to build proteins, maintain cell membranes, fire neurons, and keep your body temperature stable. Without this constant flow of energy, you would die. Life is, at its core, a process of channeling energy to maintain order. Does the universe do something similar? In a sense, yes. The universe is not a static, unchanging thing. It is a dynamic system, constantly processing energy, constantly transforming one form of energy into another. Stars convert hydrogen into helium through nuclear fusion, releasing enormous amounts of energy in the process. That energy radiates outward as light and heat, driving chemical reactions on planets, powering weather systems, and providing the energy that sustains life on Earth. Galaxies, too, are energy processing systems. They consume gas, converting it into stars. Those stars burn for millions or billions of years, producing heavier elements in their cores. When the stars die, they scatter those elements into space, where they become the raw material for new stars, new planets, and new chemistry. The galaxy is a vast metabolic engine, taking in raw material and transforming it into increasingly complex structures. And the universe as a whole is engaged in this process on the grandest possible scale. Energy flows from hot regions to cold regions, from dense regions to sparse regions, and as it flows, it creates structure. It creates galaxies and stars and planets and life and consciousness. The universe is not just sitting there. It is doing something. It is processing energy and producing complexity. That is not exactly metabolism in the biological sense, but it is remarkably similar. The physicist Eric Chyson has spent decades studying this connection. He has developed a metric called energy rate density, which measures how much energy flows through a system per unit mass per unit time. And he has found something remarkable. Over the history of the universe, the energy rate density of the most complex structures has been steadily increasing. Galaxies have a certain energy rate density. Stars have a higher one. Planets are higher still. Life is dramatically higher. And the human brain has one of the highest energy rate densities of any known structure in the universe. The universe, it seems, has been getting better and better at channeling energy into increasingly complex forms. It is as if the cosmos has a metabolism, and that metabolism is accelerating. Let us put some numbers to this, because they are striking. A galaxy, averaged across its entire mass, has an energy rate density of about half an erg per second per gram. The Sun does better, at about 2 ergs per second per gram. The Earth's surface, warmed by the Sun, manages about 75 ergs per second per gram. A plant, converting sunlight to chemical energy, achieves about 900. An animal, with its active metabolism, reaches about 20,000. And the human brain, that 3-pound organ consuming 20% of your body's energy, achieves an astonishing 150,000 ergs per second per gram. Do you see the pattern? Over the course of cosmic history, the most complex structures in the universe have been processing energy at ever-increasing rates. The trend is unmistakable. And it spans the entire history of the cosmos, from the formation of the first galaxies to the emergence of the human brain. The universe is not just generating complexity. It is generating increasingly energy-intensive complexity. It is as if the universe has a direction, a tendency, a drive towards structures that process energy faster and faster. Biologists have a word for this kind of directed energy processing. They call it metabolism. And the universe has been doing it for nearly 14 billion years. Living things grow. They start small and become large. They start simple and become complex. An acorn becomes an oak tree. A fertilized egg becomes a human being. Growth is one of the most fundamental properties of life. And the universe grows. It has been growing since the Big Bang, expanding outward in every direction, getting larger with every passing moment. But it is not just growing in size. It is growing in complexity. In the first moments after the Big Bang, the universe was a nearly uniform soup of particles and energy. There were no atoms, no molecules, no stars, no planets, no life. Just a smooth, hot fog. Over billions of years, gravity pulled matter together into increasingly complex structures. First atoms formed. Then molecules. Then clouds of gas collapsed into stars. Stars produced heavier elements. Those elements formed planets. On at least one of those planets, chemistry became biology. Biology became increasingly complex. Single-celled organisms became multicellular organisms. Simple organisms became complex organisms. And eventually, consciousness emerged. This progression from simplicity to complexity is one of the most striking features of the universe's history. It is not guaranteed by the laws of physics. The second law of thermodynamics says that overall disorder must increase. But within that general trend toward disorder, local pockets of extraordinary order can form, as long as they are paid for by greater disorder elsewhere. And the universe has been producing these pockets of order with increasing efficiency for nearly 14 billion years. The biologist Stuart Kauffman has argued that this tendency toward increasing complexity is not an accident. It is a fundamental property of the universe. Complex systems, he argues, naturally tend to become more complex over time, exploring new forms and structures with a kind of restless creativity. The universe does not just grow in size. It grows in richness, in diversity, in the depth and intricacy of its structures. That is a kind of growth that looks, in some deep sense, like the growth of a living thing. Reproduction is one of the hardest properties of life to attribute to the universe. Living things make copies of themselves. Dogs produce puppies. Cells divide. Trees release seeds. Does the universe reproduce? Obviously, we have no direct evidence that it does. We have never observed a universe giving birth to another universe. But there are speculative theories in physics that suggest it might. The physicist Lee Smolin has proposed a theory called cosmological natural selection. In this theory, black holes are the reproductive organs of the universe. When a black hole forms, Smolin suggests, it may give rise to a new universe on the other side of its event horizon, a baby universe with slightly different physical constants than its parent. If this is true, then universes that produce many black holes will have many offspring, and those offspring will, on average, inherit the tendency to produce many black holes. Over time, this process would lead to a kind of natural selection among universes. Universes that are good at producing black holes would come to dominate the population of universes, just as organisms that are good at reproducing come to dominate populations of organisms. And here is the remarkable thing: a universe that is good at producing black holes turns out to be a universe that is also good at producing stars, heavy elements, planets, and life. The properties that make a universe fertile in the black hole sense are closely related to the properties that make it hospitable to life. This is a speculative theory, and it has not been proven. It may never be proven, since we cannot observe other universes. But it is a serious scientific hypothesis, proposed by a respected physicist, and it suggests that the universe may, in some sense, be part of a larger reproductive process. If Smolin is right, our universe is not a one-off accident. It is one member of a vast, evolving population of universes, selected over countless generations for its ability to produce complexity. Even if Smolin's specific theory is wrong, the idea of cosmic reproduction appears in other forms. The eternal inflation model that we discussed in an earlier episode suggests that our universe is one of an infinite number of bubble universes, each spawned by the inflationary process. While this is not reproduction in the biological sense, since there is no selection pressure and no inheritance of traits, it does suggest that the universe has a tendency to generate more of itself. It proliferates. It expands. It fills whatever space is available with new copies and variations of itself. That is not exactly reproduction. But it is not entirely unlike it either. There is another way to think about cosmic reproduction that brings us back to the information perspective. When a living cell divides, what it really does is copy its information, its DNA, and pass it on to its daughter cells. The physical material is not what is preserved. It is the pattern, the information, that is passed on. And the universe is constantly copying patterns. Atoms form into molecules according to the same rules everywhere. Stars form and evolve through the same processes in every galaxy. The laws of physics, which are really information about how matter and energy behave, are replicated in every corner of the cosmos. The universe does not reproduce itself as a whole, but it reproduces its patterns, its rules, its information, endlessly and everywhere. In this light, every time a new star forms, it is the universe reproducing a pattern. Every time a crystal grows, every time a molecule self-assembles, every time a living organism reproduces, it is the universe copying information from one location to another. The universe is, in this sense, a vast replicating system, endlessly copying and varying its own patterns. Life, as we know it, is simply the most sophisticated version of this cosmic tendency toward replication. Living things respond to their environment. A plant turns toward the sun. An amoeba moves away from a toxic chemical. A human flinches when touched by something hot. This responsiveness, this ability to detect and react to changes in the external world, is one of the defining features of life. Does the universe respond to its environment? This is a tricky question, because it is not clear that the universe has an environment. By definition, the universe includes everything. There is nothing outside it for it to respond to. But within the universe, there is constant responsiveness. Matter responds to gravity. Atoms respond to electromagnetic forces. Particles respond to the strong and weak nuclear forces. Everything in the universe is constantly adjusting its behavior in response to everything else. And at a higher level, complex systems within the universe show sophisticated responsiveness. Ecosystems respond to changes in climate. Economies respond to changes in supply and demand. Brains respond to sensory input. These are all subsystems of the universe, and their responsiveness is, in some sense, the universe responding to itself. This is a strange and beautiful idea. The universe is not just a passive container in which things happen. It is an active, responsive system, constantly adjusting, constantly adapting, constantly reorganizing itself in response to its own internal dynamics. It is not responding to an external environment, because there is no external environment. But it is responding to itself. And that self-responsiveness, that constant internal adjustment, is one of the things that makes the universe look, at least metaphorically, like a living system. Think about what happens when a star explodes as a supernova. The shock wave from the explosion compresses nearby gas clouds, triggering the formation of new stars. Those new stars produce their own heavy elements, some of which will eventually become part of new planetary systems. The death of one star gives birth to many others. The universe responds to its own events, turning destruction into creation, death into new life. This is not a one-way process. It is a cycle, a feedback loop, in which the output of one process becomes the input for the next. Or consider how galaxies interact. When two galaxies collide, which happens regularly over cosmic timescales, the gravitational interaction triggers enormous bursts of star formation. Gas that had been sitting quietly for billions of years is suddenly compressed and ignited, producing thousands of new stars in a relatively short period. The galaxy responds to the encounter by creating. It adapts to the new conditions by producing new structures. This is responsiveness on a cosmic scale, and it looks, in its broad outlines, remarkably like the responsiveness of a living system to a change in its environment. Evolution is perhaps the most powerful and distinctive feature of life. Living things change over time. They adapt to their environments. They diversify into new forms. They become more complex, more specialized, more finely tuned to the challenges of survival. Evolution by natural selection is the engine that drives the diversity and complexity of life on Earth. Does the universe evolve? Not in the strict Darwinian sense. Darwinian evolution requires reproduction with variation and selection, and the universe as a whole does not reproduce in any obvious way, except possibly through the speculative mechanisms we discussed earlier. But evolution in a broader sense, change over time, increasing complexity, diversification, the emergence of new forms, is absolutely a feature of the universe. The universe 13 billion years ago was radically different from the universe today. It has changed. It has diversified. It has produced an astonishing variety of structures, from quarks to galaxy clusters, from hydrogen atoms to human brains. And this change has a direction. It moves, on average, from simplicity to complexity, from uniformity to diversity, from potential to actuality. The universe is not just changing randomly. It is developing. It is unfolding. It is, in a very real sense, becoming. The philosopher Alfred North Whitehead built an entire metaphysical system around this idea. He called his philosophy process philosophy, and its central claim is that reality is not made of static things but of dynamic processes. The universe is not a collection of objects. It is a web of events, each one flowing into the next, each one building on what came before. In Whitehead's view, the universe is not a machine. It is an organism. It is alive, in the deepest possible sense, because it is constantly creating itself, constantly becoming something new. This view is not widely held among physicists, but it resonates with many biologists and philosophers who study complex systems. The universe does seem to have an inherent creativity, a tendency to produce novelty, to explore new forms, to surprise itself with what it can become. Whether we call that creativity life is, in some ways, a matter of definition. But it is remarkable, whatever we call it. Consider the sheer variety of what the universe has produced. Spiral galaxies and elliptical galaxies. Red giants and white dwarfs. Gas planets and rocky planets. Oceans of liquid water and lakes of liquid methane. Volcanoes that erupt ice and storms that rain diamonds. Single-celled organisms and blue whales. coral reefs and neural networks, Beethoven symphonies and mathematical proofs. All of this has emerged from a universe that started as a nearly uniform soup of hydrogen and helium. The creativity of the cosmos is breathtaking. It is as if the universe is an artist, endlessly experimenting with new forms, new combinations, new ways of organizing matter and energy into patterns that have never existed before. And this creativity shows no signs of slowing down. Right now, on this planet, human beings are creating new forms of complexity that the universe has never seen before: computers, the internet, artificial intelligence, genetic engineering. We are extending the creative capacity of the cosmos into new domains, building structures and systems that nature never produced on its own. In a very real sense, the universe's creativity is accelerating. Through us, through technology, through culture, the universe is finding new ways to organize itself, new forms of complexity, new patterns that were not possible before the emergence of intelligent, tool-using beings. The universe is not finished creating. It is, if anything, just getting started. There is a deep connection between life and thermodynamics, the branch of physics that deals with energy, entropy, and the flow of heat. And this connection illuminates our question in a powerful way. As we discussed in an earlier episode, the second law of thermodynamics says that entropy, the measure of disorder in a system, tends to increase over time. The universe is moving, overall, from order to disorder, from structure to randomness. This seems to be the opposite of what life does. Life creates order. Life builds structure. Life takes simple molecules and assembles them into extraordinarily complex organisms. How is this possible in a universe that is supposed to be running down? The answer, as we have noted, is that life creates local order at the expense of greater disorder elsewhere. Your body maintains its exquisite internal order by consuming food and radiating heat, increasing the entropy of the environment by more than it decreases the entropy inside your body. Life does not violate the second law. It rides the second law, using the flow of energy from hot to cold, from ordered to disordered, to power the creation of local complexity. But here is the fascinating part. The physicist Jeremy England has proposed a theory that goes further. England suggests that the formation of lifelike structures may not just be compatible with the second law. It may be driven by it. His theory, called dissipation-driven adaptation, suggests that matter naturally tends to organize itself into structures that are good at dissipating energy, at spreading it out, at increasing entropy. And the structures that are best at dissipating energy turn out to be the same kinds of structures that we recognize as alive. In other words, life may not be a lucky accident that happens to be compatible with thermodynamics. Life may be what thermodynamics wants. The universe may be driven, by the deepest laws of physics, to produce structures that process energy and generate complexity. Life, in this view, is not something that happened despite the laws of physics. It is something that happened because of them. If England is right, then life is not an anomaly in the universe. It is a natural and perhaps inevitable consequence of the way energy flows through matter. The universe is not a dead machine that accidentally produced life. It is a system whose fundamental dynamics naturally and inevitably lead to the emergence of living things. The universe does not just contain life. It tends toward life. It is, in some deep thermodynamic sense, alive. There is a concept in science that is central to our question tonight, and it is worth exploring in some depth. That concept is self-organization. Self-organization is the process by which order and structure emerge spontaneously from disorder without any external guiding hand. No one tells water molecules to form a snowflake. They do it on their own, guided by nothing more than the laws of physics and the conditions of their environment. The hexagonal symmetry of a snowflake is not designed. It emerges. Self-organization is everywhere in nature. Sand dunes form in deserts without anyone shaping them. Convection cells form in heated fluids without anyone stirring them. Termite mounds, some of which are extraordinarily complex structures with ventilation systems and temperature regulation, are built by individual termites following simple rules, with no architect and no blueprint. The complexity of the mound emerges from the interactions of thousands of simple agents. And self-organization operates at every scale in the universe. Atoms self-organize into crystals. Molecules self-organize into cell membranes. Cells self-organize into tissues and organs. Organisms self-organize into ecosystems. Stars self-organize into galaxies. Galaxies self-organize into the cosmic web. At every level, from the smallest to the largest, the universe spontaneously generates order and structure from disorder and chaos. The physicist Ilya Prigogine won the Nobel Prize in Chemistry for his work on what he called dissipative structures, systems that maintain their organization by dissipating energy. A candle flame is a dissipative structure. So is a hurricane. So is a living cell. So, in a sense, is a star. These systems exist far from thermodynamic equilibrium, in a state of constant flux, constantly processing energy, constantly maintaining their structure against the tendency of the universe toward disorder. They are islands of order in a sea of entropy, sustained not by any external force but by the flow of energy through them. Prigogine showed that these dissipative structures can spontaneously become more complex over time. Under the right conditions, a simple dissipative structure can give rise to a more complex one, which can give rise to an even more complex one, and so on. Complexity breeds complexity. Order breeds order. The universe, driven by the flow of energy and the laws of thermodynamics, naturally ratchets itself toward higher and higher levels of organization. This is a profound insight. It means that the complexity we see in the universe, the galaxies, the stars, the planets, the ecosystems, the civilizations, is not a fluke. It is not an accident. It is the natural, inevitable result of the way energy flows through matter in a universe that started in a low entropy state. The universe is a complexity-generating machine. And the most complex things it has generated, so far, are alive. If this is true, then life is not something that happened to the universe. Life is something the universe does. It is one of the universe's most characteristic activities, as natural and as inevitable as gravity, as nuclear fusion, as the expansion of space. The universe makes galaxies, and it makes life. Both are expressions of the same underlying tendency toward self-organization and increasing complexity. There is another lens through which we can examine our question, and it comes from the field of information theory. In recent decades, physicists have increasingly come to see information as fundamental to the nature of reality. Not just as something that describes the universe, but as something the universe is made of. The physicist John Archibald Wheeler, whom we met in a previous episode, coined the phrase lit from bit. He meant that every particle, every field, every physical quantity derives its existence from information. The universe, at its most fundamental level, is not made of matter or energy. It is made of information. Bits. Binary choices. Yes or no. The physical world is informational at its core. If this is true, then the universe is not just processing energy. It is processing information. Every physical interaction, every collision between particles, every exchange of photons, is a computation. The universe is computing. It is taking in information, transforming it, and producing output. And this is exactly what living systems do. Life, at its core, is an information processing system. DNA is a code. Cells are molecular computers. Brains are information processing networks. If the universe itself is an information processing system, then the difference between the universe and a living organism is not one of kind but of degree. The physicist Seth Lloyd has calculated that the universe has performed approximately 10 to the power of 120 computational operations since the Big Bang. That is an inconceivably large number. The universe is, by any measure, the most powerful computer that exists. And it has been computing, without pause, for nearly 14 billion years. The structures we see around us, the galaxies, the stars, the planets, the ecosystems, the civilizations, are all outputs of that computation. They are what the universe has calculated so far. Living things are part of that computation. They are subroutines within the cosmic program, local concentrations of information processing that feed back into the larger computation. Your brain, processing billions of bits of information every second, is one of the most intense concentrations of computation in the known universe. And it is doing something that the universe has never done before. It is processing information about itself. It is the universe becoming aware of its own computation. There is another property of living systems that we have not yet discussed, and it is deeply relevant to our question. Living things have memory. They store information about their past and use it to guide their future behavior. Your DNA is a memory, a record of billions of years of evolutionary history encoded in molecules. Your brain is a memory, storing the experiences of your lifetime in patterns of neural connections. Memory is what allows living things to learn, to adapt, to improve over time. Does the universe have memory? In a sense, it does. The current state of the universe is a record of everything that has happened since the Big Bang. The cosmic microwave background radiation, which we discussed in our first episode, is a memory of the early universe, an imprint of conditions that existed nearly 14 billion years ago, still visible in every direction you look. The chemical composition of a star is a memory of the gas cloud from which it formed. The geological layers of the Earth are a memory of billions of years of planetary history. Fossils are memories of organisms that lived and died millions of years ago. The universe does not just process information. It stores it. Every event that occurs leaves a trace, an imprint on the fabric of reality. The universe is, in this sense, a vast archive, a record of its own history, encoded in the positions of stars, the composition of rocks, the patterns of cosmic radiation, and the structures of living things. And this archive is not passive. It feeds back into the ongoing processes of the universe, influencing what happens next. The heavy elements produced by ancient stars become the building blocks of new planets. The genes inherited from ancient organisms shape the bodies and behaviors of modern ones. The past influences the present, and the present will influence the future. This is exactly what memory does in a living system. And there are feedback loops in the universe that resemble the feedback loops in living organisms. Stars produce heavy elements, which allow the formation of planets, which provide the environments where complex chemistry can occur, which leads to life, which transforms the chemistry of its planet, which changes the conditions for future life. Each stage in this process feeds back into the system, changing the conditions for the next stage. The universe is not a linear sequence of events. It is a web of feedback loops, each one influencing and being influenced by the others. This is the hallmark of a complex, adaptive system. This is what living things do. Before we zoom back out to the scale of the cosmos, let us spend a moment at a middle scale, the scale of our own planet. Because there is a beautiful and controversial idea about life at this scale that is relevant to our question. In the 1970s, the scientist James Lovelock proposed the Gaia hypothesis. Named after the Greek goddess of the earth, the Gaia hypothesis suggests that the earth itself behaves like a living organism. Not that the earth is literally alive in the biological sense, but that the complex interactions between the atmosphere, the oceans, the geology, and the biosphere create a self-regulating system that maintains conditions favorable for life. Consider, for example, the composition of the atmosphere. The Earth's atmosphere contains about 21% oxygen. This is a remarkably convenient concentration for life. too much oxygen and fires would burn uncontrollably. Too little, and complex animals could not survive. And yet, this concentration has remained roughly stable for hundreds of millions of years, despite the fact that oxygen is a highly reactive gas that would quickly disappear from the atmosphere if living things were not constantly producing it through photosynthesis. The temperature of the Earth, too, has remained within a narrow range that is compatible with liquid water and with life, even though the Sun has been getting gradually brighter over billions of years. The Earth has compensated for the increasing solar output through a complex feedback loop involving carbon dioxide, weathering of rocks, ocean chemistry, and biological processes. It is as if the Earth has a thermostat, a mechanism for maintaining a stable internal temperature in the face of changing external conditions. This is homeostasis, one of the defining properties of life. The Earth, through the interplay of its living and non-living components, maintains a stable internal state. It regulates itself. It responds to perturbations and returns to equilibrium. It behaves, in this respect, like a living organism. The Gaia hypothesis has been controversial since it was first proposed. Many scientists have criticized it as teleological, as implying that the Earth has a purpose or an intention. But a weaker version of the hypothesis, sometimes called Gaia theory, has gained broader acceptance. This version does not claim that the Earth is literally alive or that it has goals. It simply observes that the Earth system, the coupled system of life, atmosphere, oceans, and geology, has emergent properties that look like the properties of a living system. Self-regulation. Homeostasis. The maintenance of conditions favorable for the persistence of the system as a whole. If the Earth can be seen as a kind of living system, what about the universe as a whole? The universe, too, is a complex system with emergent properties. It, too, produces structures that maintain themselves against the background of increasing entropy. It, too, processes energy and generates complexity. The Gaia hypothesis, applied at the cosmic scale, suggests that the universe might be a self-organizing, self-maintaining system, one that naturally produces the conditions for its own increasing complexity. There is another example of planetary self-regulation that is worth considering. The salinity of the oceans has remained remarkably stable for hundreds of millions of years, even though rivers constantly wash salt into the sea. Some mechanism, involving biological and geological processes, removes salt at roughly the same rate it is added. The pH of the ocean, too, has remained within a narrow range compatible with life. These are not accidents. They are the results of complex feedback loops involving living organisms, ocean chemistry, and geological processes, all working together to maintain a stable environment. The Earth, in short, behaves like a thermostat, a regulatory system that detects deviations from its optimal state and corrects them. This is exactly what living cells do. Your body detects when your blood sugar is too high and releases insulin. It detects when your temperature is too low and makes you shiver. The Earth does the same thing, just on a vastly larger scale and vastly longer timescale. And if the Earth can do this, perhaps the universe can too, in ways that we have not yet recognized or understood. Let us take a step further into speculation. Several thinkers, from different disciplines, have argued that the universe does not just resemble a living organism in certain ways. They have argued that it is one. The idea that the universe is a living being has ancient roots. Many indigenous cultures around the world view the cosmos as alive, as animated by spirit or consciousness. In Hinduism, the universe is sometimes described as the body of Brahman, the ultimate reality. In Taoism, the Tao is the living principle that animates all things. These are not scientific theories, but they reflect a deep human intuition that the cosmos is not dead matter but a living whole. In modern science, this intuition has been given new form by thinkers like Whitehead, whom we mentioned earlier, and by physicists and biologists who study complex systems. The mathematician and biologist Brian Goodwin argued that life is a property of organization, not of material. Any system that is organized in the right way, with the right kind of feedback loops and energy flows, is alive, regardless of what it is made of. If the universe has the right kind of organization, then the universe is alive. The cosmologist Lee Smolin, whose theory of cosmological natural selection we discussed earlier, has described the universe as a self-organizing system that naturally tends toward increasing complexity. He compares the universe to a living ecosystem, in which new forms of organization constantly emerge and interact, producing ever more intricate and beautiful structures. The universe, in Smolin's view, is not a machine. It is a creative process, one that is constantly inventing new ways of being. And there are structural similarities between the universe and living organisms that are worth noting. The cosmic web, the vast network of filaments and nodes that forms the large-scale structure of the universe, looks remarkably similar to the neural network of a brain. This is not just a superficial resemblance. Studies have shown that the mathematical properties of the cosmic web and the neural network of the brain are strikingly similar, with comparable levels of complexity, comparable distributions of connections, and comparable information processing capacity. The universe, at its largest scale, is organized like a brain. What that means, if anything, is an open question. But it is a provocative one. In 2020, a team of astrophysicists and neuroscientists published a remarkable paper comparing the structure of the cosmic web with the structure of the human brain. They found that the two systems, despite differing in scale by about 27 orders of magnitude, share a strikingly similar architecture. Both consist of networks of filaments and nodes. Both have similar spectral density distributions. Both have a similar ratio of matter to connecting filaments. The researchers estimated that the cosmic web contains about 10 to the power of 24 connections between galaxy clusters, while the human brain contains about 10 to the power of 14 connections between neurons. Despite the vast difference in scale, the organizational principles are eerily similar. What should we make of this? It might be a coincidence. It might be that network structures of this kind are simply the most efficient way to organize complex systems, regardless of whether those systems are made of neurons or galaxies. But it might also be hinting at something deeper. It might be that the universe, at every scale, naturally organizes itself according to the same fundamental principles that, at the biological scale, we recognize as the architecture of intelligence and consciousness. The universe might be, in some structural sense, a mind. Not a human mind. Not a mind that thinks in words or Sol's equations. But a mind in the sense of a vast, interconnected information processing network, organized in a way that is eerily similar to the organ that produces consciousness in human beings. We have been exploring whether the universe has the physical properties of a living system. But there is a deeper question lurking beneath the surface, one that we touched on in our last episode. Does the universe have experience? Is it conscious? This is the question that transforms our inquiry from a matter of definition into a matter of profound philosophical significance. A system that processes energy and generates complexity might be called alive in a metaphorical sense. But a system that has experience, that feels, that is aware, would be alive in the fullest possible sense. We have already discussed panpsychism, the idea that consciousness is a fundamental feature of reality, present in some form in every physical system. If panpsychism is true, then every atom, every field, every interaction in the universe has some tiny flicker of experience associated with it. And the more complex the system, the richer the experience. A rock has a vanishingly simple form of experience. A bacterium has a slightly richer one. An insect has more. A mammal has more still. A human brain, with its billions of interconnected neurons, has the richest experience we know of. But what about the universe as a whole? If every part of the universe has some form of experience, does the whole have an experience that is greater than the sum of its parts? Is there something it is like to be the universe? The philosopher Philip Goff has explored this question in depth. He argues that if panpsychism is true, then there is no principled reason to deny that the universe as a whole might be conscious. The universe is, after all, the most complex system there is. If complexity gives rise to richer forms of experience, then the universe might have the richest experience of all. Not a human-like consciousness, not a consciousness that thinks in words or sees in images, but something vast and alien and utterly beyond our comprehension. Something that encompasses every experience that has ever occurred, every sensation, every thought, every dream, woven together into a cosmic awareness that includes everything. This is a mind-bending idea, and it is impossible to prove or disprove with current science. But it is worth sitting with for a moment, especially as you lie here in the dark, drifting toward sleep. The possibility that the universe is not just alive but aware. That it is not just processing energy and information but experiencing something. That the darkness around you, the stars above you, the atoms inside you, are all part of a single, vast, living awareness. Whether or not this is true, it is a beautiful idea. And beauty, as the physicist Paul Dirac once said, is often a reliable guide to truth in physics. There is one more perspective on cosmic consciousness that is worth exploring. The neuroscientist Giulio Tononi has developed a theory of consciousness called Integrated Information Theory, or IIT. In this theory, consciousness is not something that only brains can have. It is a property of any system that integrates information in a certain way. The more information a system integrates, the more conscious it is. A photodiode has a tiny amount of integrated information, and therefore a tiny flicker of consciousness. A brain has an enormous amount, and therefore a rich, vivid consciousness. Tononi's theory provides a mathematical framework for measuring consciousness, a quantity he calls phi. And in principle, phi can be calculated for any system, not just brains. A thermostat has a small phi. A worm has a larger phi. A human brain has a very large phi. And the universe as a whole, if its parts are sufficiently integrated, might have a phi that dwarfs anything we have encountered. The key question is whether the universe's parts are sufficiently integrated. In a brain, every neuron is connected to thousands of others, and information flows rapidly between them. In the universe, galaxies are separated by vast distances, and information cannot travel faster than light. This might mean that the universe, despite its enormous size and complexity, is not very integrated, and therefore not very conscious, by Tononi's measure. But within smaller regions, within galaxy clusters, within solar systems, within planets, the level of integration is much higher. And within brains, the integration is higher still. Perhaps consciousness in the universe is not distributed evenly. Perhaps it is concentrated in pockets, in the brains of living beings scattered across the cosmos, like sparks of awareness scattered across a dark landscape. Each spark is the universe experiencing itself in one particular place, from one particular perspective. And together, all those sparks, all those moments of awareness, all those experiences, form the universe's total experience of itself. Not a single unified consciousness, but a vast, scattered, multifaceted awareness, like the universe looking at itself through billions of eyes at once. We have been exploring the question of whether the universe is alive from a scientific perspective, looking at metabolism, growth, reproduction, responsiveness, evolution, thermodynamics, information, and consciousness. And we have found that the answer is not a simple yes or no. It depends on how you define life, on which properties you consider essential, and on how willing you are to extend biological concepts to cosmological scales. But there is another way to approach the question, and it is a way that may be more appropriate for a night like this, when you are lying in the dark, letting your thoughts soften and blur. There is a poetic truth to the idea that the universe is alive. A truth that does not depend on precise definitions or rigorous arguments. A truth that is felt rather than proved. You are alive. You know this with absolute certainty. You feel the warmth of your body, the rhythm of your breathing, the quiet hum of your consciousness. You are alive. And you are made entirely of the universe. Every atom in your body is a universe atom. Every process in your cells is a universe process. Every thought in your mind is a universe thought. You are not something separate from the universe that happens to be alive. You are the universe, and you are alive. Therefore, the universe is alive. At least the part of it that is you. And you are not the only living part. Every bacterium, every plant, every animal, every living thing on Earth is the universe being alive. And if life exists on other planets, in other solar systems, in other galaxies, then the universe is alive in even more places, in even more ways. The universe is not a dead thing that accidentally produced life. It is a thing that is alive, in scattered pockets, spread across billions of light years, and those pockets of life are not separate from the cosmos. They are the cosmos. They are the universe, experiencing itself, knowing itself, wondering about itself. Carl Sagan said it best. We are a way for the cosmos to know itself. And if the cosmos can know itself, if it can produce beings that wonder and dream and ask whether the universe is alive, then perhaps the question answers itself. The universe is alive because you are alive. And you are the universe. If the universe has a natural tendency toward life, as the physics of self-organization and thermodynamics suggest, then a profound prediction follows: life should not be confined to Earth. It should be common throughout the cosmos. We do not yet have direct evidence of life beyond Earth. But the conditions for life, as far as we understand them, appear to be widespread. Water, the solvent that life on Earth depends on, is one of the most common molecules in the universe. The chemical elements that make up living things, carbon, hydrogen, oxygen, nitrogen, are among the most abundant elements in the cosmos. And the organic molecules that are the building blocks of life have been found in meteorites, in comets, in interstellar gas clouds, and in the atmospheres of other planets. The raw ingredients for life are everywhere. Our own solar system contains several places where life might exist. Europa, a moon of Jupiter, has a liquid water ocean beneath its icy surface, heated by tidal forces from Jupiter's gravity. Enceladus, a moon of Saturn, has geysers that shoot water vapor and organic molecules into space, suggesting a warm, chemically rich ocean beneath its ice. Even Mars, cold and dry as it is today, may have harbored life billions of years ago when it had liquid water on its surface, and some scientists believe that microbial life might still persist deep underground. Beyond our solar system, astronomers have discovered thousands of exoplanets, planets orbiting other stars. Many of these are in the habitable zone, the range of distances from their star where liquid water could exist on the surface. The Milky Way galaxy alone may contain billions of habitable planets. And there are hundreds of billions of galaxies in the observable universe. The number of potential homes for life is staggering. If life is a natural consequence of the way the universe processes energy, then it would be strange, even suspicious, if Earth were the only place it had arisen. The laws of physics are the same everywhere in the universe. The chemistry is the same. The thermodynamics is the same. If the conditions on early Earth were sufficient for life to emerge, and if similar conditions exist on billions of other worlds, then it seems likely, perhaps inevitable, that life has emerged elsewhere. We may not have found it yet. But the universe is very large, and we have barely begun to look. And if life is common in the universe, then the universe is not just a dead expanse of matter and energy with one tiny pocket of life on one tiny planet. It is a living cosmos, teeming with biology, filled with organisms that metabolize and grow and reproduce and evolve, on countless worlds, in countless forms, across billions of light years. The universe is not a desert with one oasis. It may be a garden. And that changes everything about how we should think about the cosmos and our place in it. There is a concept in astrobiology called the Great Filter, which asks why, if the conditions for life are so common, we have not yet detected any signs of intelligent life beyond Earth. One possible answer is that the emergence of intelligence is exceedingly rare, even if simple life is common. Another is that intelligent civilizations tend to destroy themselves before they can make their presence known. But there is a more hopeful possibility. Perhaps intelligent civilizations are out there, but the universe is so vast and our instruments so primitive that we simply have not found them yet. We have been searching for only a few decades, with limited technology, in a galaxy that is 100,000 light-years across. The absence of evidence is not evidence of absence. And there is another possibility, one that is relevant to our question tonight. Perhaps the universe is in an early stage of what might be called its awakening. The universe is nearly 14 billion years old, but the conditions for complex life have existed for only a fraction of that time. The heavy elements necessary for rocky planets and complex chemistry were not abundant until several generations of stars had lived and died, which took billions of years. Life on Earth has existed for about 4 billion years, but complex multicellular life has existed for only about 600 million years. Intelligent, technologically capable life has existed for only a few thousand years, an eye blink in cosmic terms. If the universe is in the process of waking up, of becoming alive and aware, then we are witnessing the very beginning of that process. The universe is like a newborn, just opening its eyes for the first time. The pockets of consciousness that exist now, on Earth and perhaps on other worlds, are the first stirrings of a cosmic awareness that may one day encompass the entire cosmos. We are not the end product of the universe's evolution. We are the beginning. The universe is just starting to become alive. And the best is yet to come. Let us look forward for a moment. If the universe has a tendency toward life, toward complexity, toward awareness, what does the future hold? In the short term, cosmically speaking, life on Earth will continue to evolve and diversify. New species will emerge. Ecosystems will shift and change. And if humanity survives its current challenges, we may spread to other planets, other star systems, perhaps other galaxies. Life, which began as simple chemistry on a single planet, could eventually spread across the cosmos, transforming dead matter into living systems wherever it goes. The physicist Freeman Dyson imagined a future in which intelligence finds ways to survive even as the universe cools and expands. He suggested that thinking beings could slow their thought processes down, using less and less energy, stretching their subjective experience over ever longer periods of cosmic time. In this scenario, consciousness could persist indefinitely, even as the stars burn out and the universe grows cold. Life would adapt to the changing conditions of the cosmos, just as it has adapted to every change in conditions on Earth. The cosmologist Frank Tipler went even further. He proposed a theory he called the omega point, in which intelligent life eventually gains control of the entire universe, steering its evolution toward a final state of infinite complexity and infinite consciousness. In Tipler's vision, the universe does not end in heat death. It ends in a blaze of life, a cosmic awakening in which the universe becomes fully alive, fully aware, fully realized. These are speculative visions, and they may not come to pass. The universe may indeed end in heat death, in the cold, dark, lifeless state we described in an earlier episode. But even if it does, the fact that the universe produced life at all, that it produced consciousness, that it produced beings who could imagine the omega point and wonder about the nature of cosmic life, is itself extraordinary. The universe may not be alive forever. But it has been alive. And that is no small thing. There is a beautiful thought experiment that captures the significance of this. Imagine two universes. One universe follows the same physical laws as ours, has the same Big Bang, the same expansion, the same galaxy formation, but by some fluke, life never emerges. It goes through all the motions, stars burning, galaxies spinning, but nobody is there to see it, to feel it, to wonder about it. The other universe is ours, where life did emerge, where consciousness did arise, where beings do look up at the sky and ask these questions. Which universe is more interesting? Which universe is more meaningful? In terms of physics, they might be identical in every measurable respect except for the presence of life. But the difference that life makes is incalculable. Life transforms the universe from a process into a story, from an event into an experience, from something that happens into something that matters. And if that is what life does, then the universe that contains life is not just slightly different from the one that does not. It is fundamentally, qualitatively, immeasurably different. Life does not just exist within the universe. It transforms the universe. It gives the universe meaning. And a universe with meaning is a very different kind of universe from one without. So even if the universe is not alive in a technical biological sense, the life it contains transforms it into something that functions, in the deepest way, like a living thing. A universe with life is a universe that knows itself, that feels itself, that wonders about itself. And that knowing, that feeling, that wondering, is what makes a universe alive in the way that truly matters. So is the universe alive? The honest answer is that we do not know. It depends on definitions that we have not yet settled and on facts that we have not yet discovered. But the question itself has taken us on a remarkable journey tonight. We have seen that the universe processes energy like a living thing. It grows and becomes more complex like a living thing. It may reproduce through black holes or inflation like a living thing. It responds to itself, adjusting and reorganizing like a living thing. It evolves, changing over time and producing new forms like a living thing. Its thermodynamics may naturally drive it toward life. It processes information on a cosmic scale. And it may even be conscious if panpsychism is true. None of this proves that the universe is alive. But it suggests that the boundary between the living and the non-living is not as clear as we thought. It suggests that life is not an anomaly, not a freak accident, but a natural expression of what the universe does. The universe produces life the way rivers produce currents, the way fires produce heat, the way storms produce lightning. It is what the universe does. It may be what the universe is. There is something else that the universe does, something that living things do and that we rarely attribute to non-living things. The universe creates beauty. Think about what the universe has produced. The spiral arms of a galaxy, curving gracefully through space. The rings of Saturn, impossibly delicate and perfectly proportioned. The aurora borealis, painting the night sky in curtains of green and purple light. A sunset, the ordinary miracle of light scattered through the atmosphere, producing colors that have moved human beings to tears for as long as there have been human beings to see them. None of these things were designed to be beautiful. There is no cosmic artist arranging the spiral arms of galaxies for aesthetic effect. And yet, they are beautiful. Profoundly, achingly, almost unbearably beautiful. The universe, following nothing more than the laws of physics, produces structures that strike conscious beings as beautiful. Why? One possible answer is that beauty is not in the eye of the beholder. It is in the structure of reality. The patterns that we find beautiful, symmetry, harmony, proportion, fractal self-similarity, are the same patterns that appear naturally when the laws of physics play out over time. Our sense of beauty may be tuned, by evolution, to respond to the deep mathematical structures of the universe. We find the universe beautiful because we are part of the universe, and our aesthetic sense has been shaped by the same laws that shape galaxies and snowflakes and sunsets. If this is true, then beauty is not a human invention. It is a property of the cosmos. The universe is beautiful in the same way that it is ordered, in the same way that it is complex, in the same way that it processes energy and information. Beauty is one of the things the universe does. And a universe that creates beauty, that produces structures so exquisite that they move conscious beings to wonder and to tears, is a universe that looks, in yet another way, like a living thing. Living things create beauty. Birds create songs. Spiders create webs. Flowers create patterns of color that attract pollinators. And the universe creates spiral galaxies and snowflakes and the cosmic microwave background and the double helix of DNA. The universe is an artist. It may be the greatest artist there is. And an artist, whatever else it may be, is alive. This is not a scientific argument. It is a poetic one. But sometimes poetry sees things that science misses. Sometimes the most important truths are the ones that can only be felt, not proved. And the truth that the universe is beautiful, that it creates beauty naturally and abundantly and without any apparent effort, is one of those truths. And whether or not the universe is alive in any technical sense, you are alive. You are here. You are conscious. You are a part of the universe that has woken up, that has opened its eyes, that has begun to ask questions about its own nature. That is extraordinary. That is miraculous, in the deepest sense of the word. The universe, through you, is experiencing itself. And that experience, your experience, right now, lying here in the dark, is one of the most precious things in all of existence. So let the question rest now. Let it settle like dust in still air. You do not need to answer it tonight. You do not need to decide whether the universe is alive or dead, conscious or unconscious, purposeful or accidental. You just need to breathe. You just need to rest. You just need to let the night hold you. The universe has been doing its thing for nearly 14 billion years. It has been processing energy, building complexity, producing stars and planets and life and minds. It has been doing all of this without any help from you. And it will continue to do it while you sleep. The galaxies will keep turning. The stars will keep burning. Somewhere, right now, a new star is being born. Somewhere, a planet is forming. Somewhere, perhaps, life is taking its first tentative steps. The universe is busy. And you have earned your rest. Think of yourself as a tiny, warm, living node in a vast cosmic network. Connected to everything. Made of everything. Part of everything. The atoms in your body were forged in stars. The energy that powers your thoughts came from the sun. The oxygen in your lungs was produced by ancient organisms that lived and died billions of years before you were born. You are woven into the fabric of the universe so deeply that it is impossible to say where the universe ends and you begin. And if the universe is alive, then your sleep is the universe sleeping. Your dreams are the universe dreaming. Your breathing is the universe breathing. There is no separation. There never was. You are the cosmos, resting after a long day of being alive. Right now, as you lie here, the universe is doing extraordinary things. In the core of a star 1,000 light-years away, hydrogen atoms are fusing into helium, releasing the energy that will travel through space for centuries before reaching some distant planet. In a nebula on the other side of the galaxy, a cloud of gas is beginning to collapse under its own gravity, starting the process that will eventually produce a new star and perhaps new planets. On the ocean floor of a moon orbiting Jupiter, hydrothermal vents may be pumping warm water into a dark sea, providing the energy that might sustain alien life. All of this is happening right now, as you breathe, as you rest, as your eyelids grow heavy. The universe never stops. It never rests. It is always creating, always transforming, always becoming. But you can rest. You have been a part of the universe's grand project today. Every thought you have had, every breath you have taken, every moment of consciousness you have experienced. You have done your part. You have been the universe being alive. And now it is time to let go, to let the deeper rhythms of the cosmos carry you into sleep. Let your muscles relax. Let your thoughts dissolve. Let the boundary between you and the universe grow soft and permeable. You are safe. You are held. You are part of something vast and ancient and ongoing. And whatever the universe is, alive or not, it has produced you. And you are beautiful. Close your eyes. Let the universe carry you into sleep. And dream of stars. Good night.